Okay, so lesson 4, week 4 for summer is going to be over rational functions. And the good news, guys and girls, is that you're not going to have to be as specific as you were back in pre-cal. A rational function, just as a refresher, the parent rational function is the one that looks like this. It's 1 over x, and there were asymptotes everywhere. A vertical and a horizontal, and this is going to be a spin-off of the parent 1 over x. Now, they're not always that easy, right? Sometimes they're like really, really ridiculous, and you have to figure out where all the asymptotes go, and sometimes there's even more than one vertical asymptote, and sometimes they even have holes. So we're going to talk about all of that in this video. Now, for simplifying expressions, I just want to show you one expression for multiplication and one expression for addition or subtraction, just as a refresher, because if you are in the middle of your algebra and you're mathing somewhere along the way and you have something like, let's say you end up with, like, 3 plus x over, x squared minus 4, and then you end up having to multiply that by x plus 2 over, like, let's say 6 plus 2x. Okay, something like this. When you see this, I just want you to remember how to deal with it, okay? Because I do not want you multiplying out the top and multiplying out the bottom. Nobody wants that. Instead, this was the deal where you need to factor things if you can. So like x squared minus 4 could be x plus 2 times x minus 2. And the reason you do this is because you're probably already seeing it. You can cancel now the x plus 2's. And then over here you could take a 2 out and have 3 plus x. And when you do that, now you can cancel these. So this is just a refresher on that sort of a topic, okay? Notice there's just a 1 on top now. Please don't forget to put that. But that would be your final answer. So remember, with multiplication or division, you want to go with the whole factor and cancel method. Now, if you are adding or subtracting, you need to go for the least common denominator, and you do want to combine these if at all possible. So I'm actually going to use a very similar problem to the one I just did. Let me keep all that the same, and instead, you know what, this will be a minus. Let's change that to a minus, and let's go like x minus 2 over x plus 1, something like that. Okay, so if we have something like this, the least common denominator, you do need to think in your head about the fact that this is really x plus 2 times x minus 2. So you could think of it like that. And then the least common denominator, you just need to make sure that all factors are accounted for in your new denominator. So the common denominator, well, they both need to have an x plus 2, and they both need to have an x minus 2. Okay? And so this one, I didn't have to add anything to the bottom of this, so this numerator gets to stay the same. I'm going to recopy this minus, and now behind it is going to be this x plus 1, but also this denominator was missing the x plus 2, so I need to make sure that it has an x plus 2 as well. So this is hopefully coming back to you now. The goal, unfortunately, is FOIL all this mess out and then subtract it, and you'll get your final answer. So I'm going to shut up and just kind of math it, and you do the same. See if we get the same thing when we work out our numerator. Okay, I think I did mine right. So my final answer would be right here. I just distributed the negative sign into my trinomial. Then I combine like terms, and this is what I'm getting. Hopefully I did that right. Let me know if I did it wrong, but that's sort of the goal there. Okay, now for the more interesting stuff. This comes up occasionally in calculus, okay? and these are usually harder than the ones that you'll see, but what you're about to see is going to be a common theme throughout the whole year, okay? And that is an idea about knowing whether you're dealing with the whole or an asymptote, and also end behavior asymptotes are going to be really important. So let's just take notes on this side as to what you do with what, and then let's do examples over here, okay? So here's the deal, wholes versus asymptotes. Okay, if you have a rational expression or a rational function and a factor cancels out, a factor can cancel out, then you have found the whole, my friends, okay? So we'll do an example in a second, but that's what I'm talking about. If you've got a rational function and the factor can cancel out, then that would be a whole. Now, if, however, you have already canceled and done all that, a vertical asymptote is going to be formed whenever your fraction is undefined, okay? So a vertical asymptote means that your fraction is undefined. Now, when is a fraction undefined? It's when the denominator is equal to 0. So if you just take your fraction and set your denominator equal to 0, you will find all of your vertical asymptotes, okay? And so as an example, let's jump over here and do an example. If I give you a function like this, let's say, ooh, crazy. Let's go x squared minus 9, and then let's go like x squared plus 5x plus 6. Okay, so this is a rational function because it can be written as a fraction. It is nothing like, or maybe I don't say nothing, it's not like the parent function because it's not just a number over x. I mean, there's all kinds of stuff going on. So the approach you would need to take is go ahead and look at the factors if it's possible to find them. So I'm just redoing this problem, rewriting it in factored form. And the point for doing that is because if you're being asked about a whole or a vertical asymptote, it really is as simple as, does something cancel on the bottom? Well, yes, it does. X plus 3 canceled, and so because x plus 3 is the factor that canceled, then the whole is that x is negative 3. There will be a whole there, okay? Now, whatever is left in the denominator, you can set equal to 0, and that will be your vertical asymptote. So my vertical asymptote will be when x is negative 2. So I'm setting that to 0. Of course, that also changed signs because I was setting it to 0 after I canceled it out. Okay, so that's how you distinguish between a whole and a vertical asymptote. You probably won't even have to graph these in calculus. You might have to look on a calculator at some point, but you usually don't have to graph them by hand. You just have to know the difference between wholes and asymptotes. Now, these functions, if you remember from up here, from the parent, these also have horizontal asymptotes. Now, last year, your teacher may have called them horizontal asymptotes. If it was a slant, they may have called it a slant asymptote, or they may have said it doesn't have an asymptote. I'm telling you, in calculus, they are called horizontal, I'm sorry, they're called end behavior. So I'm going to write back here really small, these were formerly called horizontal asymptotes or slant asymptotes. So if you remember doing that from either Algebra 2 or Pre-Cal, that's the same thing that we're going to do right now. It's just we're calling them end behavior asymptotes. They are going to tie into calculus. This is another note you might want to make. They're going to tie into calculus whenever you're analyzing the limit as x goes to infinity. So that might ring a bell. If not, we'll do it later this summer. No big deal. All right, so let's write down the rules for end behavior asymptotes. The way that I do this is I compare the powers of my rational expression. I compare the powers, and that's going to tell me what's going to happen. So, in other words, if your denominator has a higher power than your numerator, Okay, so there we go. The denominator has a greater power than your numerator. You are going to have a slant asymptote. And the way that you have to find these are the sucky ones. I don't like these, I'm not gonna lie. These are my least favorite because if the denominator, oh, I'm a liar. Ha, I'm a liar. I hope you're not writing in pen. Sorry, folks. If the denominator is greater than the numerator, actually, your asymptote will be at 0. Sorry, it'll be a horizontal asymptote. Aha, horizontal asymptote at y equals 0. These I love. These are really easy. I was thinking of the other ones whenever the numerator is greater than the denominator. These really stink because these are the ones where it will be a slant and you have to find the answer by doing long division. They're really terrible. I hate them. And then the other easy ones are if they're equal. If the power of your denominator equals the power of your numerator, then whatever the coefficients are is going to be your horizontal asymptote. Okay, so these are your 3 rules, and I'm going to just show you quickly an example of each of them, and I won't tell you which is which, but we're going to figure out what we're dealing with. So let's write down 3, and you may remember this enough that you can stop the video and try them on your own, which is awesome if you remember how to do that sort of thing. I am all for it. And how about for our last one, let's do something like that. Okay, so here we have 3 different rational functions. Hit pause, take a minute to write them down if I wrote too fast for you. But I want you to think about on all of these how to compare the powers. And the thing is, sometimes they even have multiple x's. I could have done this, in fact. Let's change that just so I prove it to you. So like some of them, like this one, the numerator has 2 different x terms, but you don't look at both. You look at the highest powered term that you see, okay? So if we're looking at the first one, in the numerator I have an x to the first, and on the bottom an x to the second. So it's a higher power in the denominator. So if the denominator is greater, then the answer for the end behavior asymptote is automatically going to be y equals 0. You don't have to think about anything else. Greater on bottom, it goes to 0. Greater on top, like in this one, that's going to stink. You don't need to look at that because there's an x squared in front of it. So we're dealing with the 2x squared over an x. Higher power in the numerator means it's a slant, and you're going to have to find that slant asymptote by doing long division. Now, sometimes you can do synthetic division. I'm going to go ahead and do long division because I want you to see what's going to happen, and then we're going to kind of make a shortcut for it. But if we were to do long division, we're going to divide that by x plus 5. X goes into 2x squared 2x times. Then we multiply what's on top by what's out front, and then we subtract it, so that goes away, and that's a negative 9x minus 1. Now x goes into negative 9x minus 1 negative 9 times, and I'm actually going to stop here because, I mean, if you wrote all this out, then you just end up with some weird remainder, okay? And we don't even care about the remainder is negligible. This is the key. This is your end behavior asymptote. So it's actually an asymptote that has an actual equation. It's going to be a line. Notice it's a line with the slope of 2. Now what's cool about calculus is that you won't always have to find this. Like sometimes you'll have to find this, but it's more important that you know that the end behavior asymptote is a slant and that you know the slant goes in the positive direction. So how could I have quickly known that it would be a slant asymptote in the positive direction? Well, if I analyze these terms again, as soon as I know that I'm doing long division, I know it's a slant. And if you look, guys, this is a positive over a positive. So guess what? That's a positive. If this had been a negative over a positive, it would be negative. negative over negative would have been positive again. So you just kind of do a sign analysis with your leading terms, and that's going to tell you what's going to happen, okay? Now for our last one, I'm looking at a negative x over a 3x. The powers match. So when the powers match, you just go for their coefficients. So this is a negative 1 over a positive 3, and that would be my asymptote. So in behavior asymptote written as a y equals, vertical asymptote written as an x equals. A whole, I wrote x equals, but it's probably a point sometimes. So whatever your teacher prefers, I'm not sure what they're going to do with that. So most of your practice problems are just going to be over these two check boxes right here, figuring out wholes, vertical asymptotes, and in behavior asymptotes. Hopefully it won't take you very long, but I'll show you more of the calculus related stuff in tutorials.